This video is going to be about parametric equations. These equations are very cool. Let's write it out. Alright, so here's the deal. Before, we had an f of x, which is your y, is equal to some function in terms of x, and we input values for x and we get output values for y. But now, a parametric equation has an x of t and a y of t, meaning in our standard viewpoint of here's a x, y point on the plane, if this point P is equal to x comma y. Now this point P is no longer just a point that's static. It now is alive, and it is now a function of t, a p of t, so x is a function of t, and y is a function of t as well. So this dot is allowed to move around in space in various times t. What do we mean by that? So let's come up with, let's say, let t range from 0 to 2 seconds. And let's let x of t equal t squared minus 1, and let's let y of t equal 2t. We can now plot, like this, the parametric equation. So here's how to graph a parametric equation. It's just like we used to do it, like a f of t table, but now we have a t, x of t, and y of t table, all right? Once we're done tabulating these results for the values 0, 1, and 2, we can graph it here on our plane. X of 0 is really 0 squared minus 1, which is a negative 1. Y of 0 is really 2 times 0, which is 0. So I'll put a negative 1 here and a 0 here. X of 1 is really 1 squared minus 1, which is 0. And y of 1 is really 2 times 1, which is a 2. Put 0, 2. And x of 2 is equal to 2 squared minus 1, which is equal to 4 minus 1, which is equal to 3. And y of 2 is equal to 2 times 2, which is equal to 4. So 3 and 4. Alright? So all this means is at time equals 0, it's at negative 1 on the x and 0 on the y. So I put a dot here. At time equals 1, it's at 0 on the x, 2 on the y. 1, 2. So it's right here. And we put a line connecting them with an arrow here. And at time equals 2, it's at positive 3 on the x. 1, 2, 3. And at positive 4 on the y. 4 here. And then it moves to here. So as you can see, parametric equations can describe a dynamic system where at time equals 0, this particle or bug or NASCAR driver or whatever it is, baseball or whatever kind of model you want to create, is moving through space, and at t equals 0 it's here, t equals 1 is here, at t equals 2 it's here. It's very, very interesting because the applications of such equations are much larger than just normal f of x is equal to y type applications. You can model things that change in a much more dynamic way. Now, after we talked about graphing, we want to talk about how to eliminate a parameter. Okay? So, another thing in this section is elimination of parameter. Right here, let's say I have x is equal to t squared minus 1 again, and our x of t, and our y of t is actually just the same over there, 2t. How do we eliminate the parameter t? Well, what you do is you solve for t, like so. Y is equal to 2 is equal to t. Then you plug this value into the other equation. So then x is equal to t squared, which ends up becoming y over 2 quantity squared minus 1. So this is equal to y squared divided by 4 minus 1. That's what x is. So if I want to solve for y in terms of x, I add a 1. So I get x plus 1 is equal to y squared divided by 4. Multiply by 4. That means I get 4x plus 4 is equal to y squared. And I take the square root. So I get y is equal to the square root of 4x plus 4. Now it's technically plus or minus, but if you want to get something that is a function, you only take the positive or the negative value. So you like to take the positive value, or else we won't get a function. The whole point of eliminating a parameter is to get a function out of a parametric equation, which typically, usually is not a function, because if something is looping in on itself, it will fail the vertical line test. Alright, that's one way to eliminate a parameter. Another situation where you eliminate a parameter can be found like this. 5 cosine of t is our x of t, and y is equal to 2 sine of t. Alright, how do we eliminate a parameter here? Well, we have to do something clever. We have to use the fact that cosine squared t plus sine squared t is equal to 1. To do so, I must multiply this by a 2 and this by a 5. Once I do that, I get 2x is equal to 10 cosine of t. And here I get 5y is equal to 10 sine of t. So that upon squaring these two values, this implies that 4x squared is equal to 100 cosine squared t, and that 25y squared is equal to 100 sine squared t, so that when I add 100 cosine squared t plus 100 sine squared t, this is equal to 4x squared plus 25y squared. Notice that moving on here to the left, I can factor out a 100 and use the Pythagorean identity. This cancels off to give me 1. And over here, I get 4x squared plus 25y squared is equal to 100. Notice that dividing both sides by 4 gives me 25 is equal to x squared plus 25 over 4 y squared. And that dividing both sides by 25 results in 1 is equal to x squared divided by 25 plus y squared divided by 4. What shape does this give? That's right. I hear you. That's correct. This is the equation for an ellipse. So somehow this parametric equation, x is equal to 5 cosine t, y is equal to 2 sine t, gave us the equation for an ellipse. So eliminating the parameters seems straightforward, solve for t, but sometimes you have to be a little clever with it. And another example is, if you have something like y is equal to x squared minus 5, and we want to create a parametric equation with the parameter t, all you got to do is set x equal to t. That would imply that our y of t is now t squared minus 5. I just replaced x with a t, and now you have a y of t. It's a parametric equation where x of t is just x is equal to t, and y of t is just x replaced with t in the original equation. That is a crash course on parametric equations at the pre-calc 2 level.